So when we are looking at tasks, right, just again, back up to the forest, right, we are operating on sentence structure, right? And these tasks really, primarily relate to the syntax and, the higher level goals of NLP, right? And what you're trying to do is, extract information. So, oh yeah, and one other thing I want to talk about, right, is name entity recognition, right? This is vital for things like chatbots, Siri, etc. Name entity recognition, or NER, it picks out, salient parts of the sentence, and it figures out the important parts like who, what, when, where, right? All right. Is everyone kind of okay with this? Okay.
I have a question.
Yeah.
I wanted to know when or for which application things like dependency parsing, chunking, and entity linking were used.
Yeah. So entity linking, for instance, is used when you have a corpus or corpora, right? And you're building sort of a knowledge graph out of this. So let's say I have um, speeches of presidents of the United States, right? And you have another, corpus, right? That is basically, documents related to famous persons and personality. Well, George Washington in one, is linked or should be linked to names of famous personalities, when they were born and so on and so forth, right? So this is where you're using entity linking to understand, meaningful insights across corpora, right? Um, Dependency parsing is still it's kind of like within the sentence or the document, right? And you're trying to understand that in my earlier example, right, I'm going home early, right? You're looking at, sorry, that's this part. So you're looking at, what are the relationships between these words, right? So entity linking has become more and more prevalent. I don't know if Ravi will have a chance to talk about knowledge graphs tomorrow. If not, we can talk a little bit more about it later. But they are actually becoming really, really critical uh, for um, uh, for understanding the world, right?
Yeah, I can say a few things, Yash, if you want.
Yeah, please.
Can you hear me?
Yeah, we can.
Yeah, sure. So the dependency graph and the entity recognitions are pretty important when you're dealing with phrases in a sentence, especially when you're parsing a legal document. An example is ownership of the house. Right. If you see the wordings, they all will look similar grammatically, but it'll be slightly different. There will be a ownership information and the type of ownership and what do they own, right? So using the dependency graph and as well as the NER, you can figure out who is the subject or who is the owners and what type of ownership. You can get to it pretty close, 85 to 90%. You can think of it is if you don't have this these models and use regex, which is regular expressions, which is what we do most of the time in language processing, that doesn't have this kind of intelligence. And using NER and this entity, the POS will actually, the dependency graph will expand. It's like regex in steroids. That's how I see it. It's a great boon to the NLP world. I hope I'm adding value to provide more information here. In the business world, if you want to search through documents and create patterns.
And you're looking at the words in each of those tokens, removing punctuation, you're looking up in a table, and then finally you are doing the lowercase on the words. Now you can actually run stemming on stop words, right? For that, again, this is a different sort of a set of stop words from the NLTK corpus, right? And here you have it, right? So one of the things that, you start to take a look at, right, is, frequency distribution of words, right? So let's try that. And here you have it, right? What were you looking at? Gulliver's Travel, right? Uh, come up. I need to go outside of this. Yeah, right. So here's a frequency distribution, right, from those words. Fine. So this is, fine, but you want to find, out the top 100 words or so, top 100 most frequent words. So this is how you do it, and then vocabulary size, and so on and so forth. So I'll actually, not go into too much detail over here. I think by now you probably get an understanding of, and you have a blank in the sentence, right? So we are going to the party blank, right? Or actually, we are blank to the party tomorrow, right? So what is that blank, right? What is a probability, associated with that blank, right? And so let's say you say that going has a higher probability of being in there. The difference with skipgram, which was proposed sometime in 2013, right, is that you take a certain part of a sentence and predict one or two words around it and give that a probability, right? So this vector-based model is really interesting, and if you get a chance, take a look at this paper, and there's some nice distillations of this paper done, because it's actually provided a very nice way of getting away from the sparse representations to a more semantic based representation of language with this model, right? And there's been evolution since then as well, right? So in early 2000, I think 13, in January, Google published a paper, and then I think in October, but just about 6 months later, they published the skipgram model. And essentially, you're mapping the word to a vector, right? And you're creating a prediction task around it, right? So given a word, what are the words around it, are should be present, right, in that context. So each input word, right, is classified into many words, right, in the dictionary. So let me now get back. Yeah, good. Okay. So let's take frequency-based approach in more detail, right? So I'm going from a higher level to a lower level, right? So we looked at frequency-based, we looked at prediction-based as these two word embedding approaches. Let's spend a little bit of time on the frequency-based approach, right? So let's say you have a document, right? And these are two representative documents, right? They're related to each other, right? The athletes were playing and Ronaldo was playing well. So in one document, you're actually representing all these words, right, in the vocabulary, but Ronaldo is not there. This is a more generic document, right? In document 2, all these generic words are not there, but a name entity, Ronaldo, is there, right? So this is basically counting how many times in each document a given word is available, right? So with, hundreds of millions of words, right, in different documents, you're basically, picking 10,000 words, right, as an alternative. Right? These are the most popular words, right? TF-IDF will actually go through this as a practical lab a little later today, right? So TF is basically the number of times a term appears in a document divided by the number of times that term is in the document, right? So here you can see, right? You can just keep counting, but it doesn't tell you proportion. What I could have 100 here, but I have no idea what that 100 count actually represents in context to what, right? And so that's why you have this, and then uh, uh, the individual document frequency, right, actually looks at the number of documents and the number of documents in which that particular term appeared. So let me motivate this, right, with an example, right? And essentially what you're doing is calculating the combination of this, the term frequency versus, IDF, right? So again, same example, right? This is, sorry, different example. this is about kids in cars. And let's say document 1 has, 2, 3, 1, and 2, frequency of these terms, right? Individual terms. You look at the total number of terms here and how frequent they are. And then you look at document 2 and you look at this. And here I've calculated TF-IDF for each one of these words, right? And this starts to give you some sense about, what that particular document is about. Okay, co-occurrence vector is, mathematically a little bit more, convoluted, but here basically you're taking similar words, right, and you're putting them together, right? So you start with, if you haven't done, matrix decomposition, that's okay, right? But essentially you're decomposing a matrix into, UNS matrices, right? And so here you have the number of terms, right? So you have all the terms that are represented as columns, and then you have the stop words, right? Over here, right? So your columns, words are here, you have your stop words here. You do SVD decomposition into UNS matrices, and then you do dimensionality reduction with PCA. So here, as I'm saying, you really calculate the number of times that words appear together in a context window, right? Right. So let's actually, again, take this with an example. You have your term here, same terms, term document over here. You have the same terms on the other side in with the stop words removed, right? And you're mapping the co-occurrence of these words, right? So let's say you're looking at co-occurrence of 2. So he is not lazy, he is intelligent, he is smart, right? And so that then converts into the number of times he and is are actually occurring together. See that? He is, right? He is. And so that's coming out there. And then
That's a different topic altogether, going to the details of how mathematically it works. Okay. Just send me a feedback. If you need me to spend time on that, maybe tomorrow first in the morning sometime, just send me a note and I'll be happy to do that. But for now, let's keep it at a high level and see how this sequence translation is done. Okay. I can see some questions here. I'll come back to this. First thing is everybody able to open this notebook in Collab? Yeah, it's all good. Very nice. Okay, so let's go through certain things. And first thing before you go, I would like you to go to wait a minute. We have to set up the GPU. I just want to set it up properly for you guys. Why am I not seeing that? Here it is. So if you see my screen, I can see a runtime here, menu, and go to change runtime type and make sure this is GPU for you, hardware accelerator, okay? And save it. Otherwise, this training will take forever, okay? Just save it. Now, for executing every one of these cells, you have to just press this button here or press shift return, right? It'll go to the next one. Okay, this is done. And just to go through this is how this is going to be done, right? So this particular sentence is a French sentence, and this is the English sentence, right? This is the actual ground truth, right? This is equal to this, whereas our model is predicting this, which is pretty close, right? Let me see whether it's slightly different. This is the actual sentence. French sentence, this is the actual translation, whereas this is the translation from the model, which is kind of she, not a poet. It's not good. Anyway, So you get the idea. So this is how these you will see the results in terms of sentences and other things. Just to get you familiar with the data here. Okay. The first step here is you import all kind of libraries, whatever is required. So you do this particular piece. Okay. And the data file loading, I actually loaded the data in the GitHub. From there, if you run the cell, it will get loaded nicely. Okay, and you can take a look at the input data here. It looks something like this. So this is the English sentences, and this is the French sentences. That's how it is set up with a tab in between. So we have to read this and get it to a format which we can use, right? So all these utilities here, here in this situation, we are not taking a token from GLOW or any predefined tokens, which we'll do it tomorrow. For BERT, we'll take the token from the BERT tokenizer. Here we are going to tokenize ourselves. Tokenization means what? You clean up all the words in all the your whole training data, clean up all the words. Then you just take the distinct set of words which is there in a dictionary. In this case, we'll create two different dictionaries. One is for input language, another is for output language. And you will see what are the total number of words available in that particular training data set. It could be 10,000 words or 20,000 words. And that becomes your dictionary, right? So you have two dictionaries. Every dictionary, you give a token for every one of the words, like 1, 2, 3. Then you're done. That's called tokenization. Then you, for every one of those tokens, you can have a word embeddings assigned in the model and train it, those kind of things, which is what is being done here. It's actually creating this class language. They're adding all the sentences, all the words, and they're actually predefining some tokens here, which is start of sentence.